Hi everyone, and welcome to today's session. So today I have the privilege of having Ganesh Kumar, who is currently at the CIPA lab at A-Star, to share about his work on how to learn biologically plausible representations for one-shot learning mechanisms. And this is actually quite cool because it is in line with my main interest, which is how do we model the brain? How do we create systems that learn fast, learn adaptively? And I can see a lot of synergies between his work and mine. So without further ado, I'll pass the time on to Ganesh Kumar to share about his work.
Great. Yeah. Thanks for the introduction, John. So hi everyone. My name is Ganesh. And yeah, it's a real pleasure meeting everyone over here. Again, I would like to thank Chongming for giving me the opportunity to share my work. So in fact, we met last year, and just from a few discussions, we quickly saw that there was a lot of overlap and exciting works to collaborate. And so I guess that's something that we've been looking forward to, and hopefully this sharing would be a good benchmark or basis for us to collaborate further.
Yeah, just to add on, Ganesh is coming from more of the neuroscience angle, while I'm actually more towards the machine learning side. So actually, I think this is a very good kind of view of like eventually modeling the brain and how we actually learn. So,
yep, yeah. So to share a bit about myself, my bachelor's degree was actually in biology, like complete wet lab biology, and I did cell experiments on like neurodegenerative diseases. But I did a bit of data analysis on animal neural data recording as well. But for my PhD, I sort of switched over to a more computational approach to understand how the brain functions. I recently graduated actually last year, and I've been working in a computer vision lab in A-Star. Actually, I just tendered, and I'm heading over to Boston for my postdoctoral training in September this year to continue working on some of these ideas. So this is because I'm particularly interested in the question of how our prior knowledge or pre-learned representations influence our subsequent learning and decision making. So the bulk of my presentation will be on my PhD thesis, and then after which we will briefly look at a computer vision project that I also recently finished. Then we can have a discussion more or less there. So at every juncture, there will be certain interim conclusions, and at that time, we can use that time to have a few questions. Okay, cool. So let's begin with my thesis, which was titled Biologically Plausible Computations Underlying One-Shot Learning of Pet Associations. So I was co-advised by Shucheng and Andrew, and also collaborated with Camilo and Cheston. So let's start with a task, right? Something that we do almost every day, or okay, maybe not every day, but every week. So imagine that we need to do grocery shopping, but in a completely new market, a market that we don't know how it is structured, how big the market is, and where the different items are placed, right? So naturally, we will explore the market and gradually learn how to navigate to the different items over several days, right? So we will walk around and then see, okay, the bread is here, the milk is here, eggs are here, apples are here, and then we'll know where the cashier is, so on and so forth. Then once we are familiar with the market, even if we have a completely new grocery list, we will be able to rapidly navigate to our goals and complete the task at hand. Right, so there's this sort of a two-dimensional approach. One is a gradual learning of the market, and then subsequently, even though the problem task has changed, but although the environment is the same, we can quickly solve it almost in one shot. So Dorothy Tse and Richard Morris, these are sort of famous people in the rodent experimental labs. So these guys developed a similar grocery shopping scenario as the rodent experiment, where rats had to navigate to a specific location in a square arena based on the flavor cue that was given to them in the start box. So the rats were in the start box, and then a flavor cue was given to them. So once the flavor cue was given to them, rats then had to learn to associate the flavor cue to one of the 6 corresponding goal locations. So this is called the multiple pet association task. So in each session, there were 6 trials, where in each trial, rats were first placed in the start box, and then they were given one of the 6 possible flavor cues. Then after some time, the rats had to navigate around the maze, and they received a reward only when they reached the location that was associated to the flavor cue that was given before. So since there are 6 possible reward locations, chance performance is 1 out of 6 or 16.7%. So because this is when the rats spend the same amount of time at the correct reward location compared to the wrong reward location. So that's the 1 out of 6 performance, which is chance. After just one session of training, we can see that the rats demonstrate chance level performance over here. But as training progressed over 20 sessions, the rats gradually learned the association task, and then they increasingly spent a higher amount of time at the correct reward location. On the 21st session, 2 of the 6 pet associations were replaced with 2 new flavor cues and 2 new reward locations. So these were 2 completely new pet associates, and they were introduced to the rats for just 1 trial each. In the subsequent session, surprisingly, the rats visited the new reward location when they were given the new flavor cues, although they only had 1 trial to learn these new pet associates. So this result demonstrates the rats' one-shot learning abilities of the 2 new flavor and location pet associations. So when either the hippocampus or the prefrontal cortex were silenced, the rats could not demonstrate this one-shot learning behavior. When the rats were also placed in a completely new environment that had different landmarks and visual cues, again, the rats could not demonstrate or transfer their one-shot learning abilities to this new environment again. So this brings us to the question, how does the brain actually perform this one-shot learning? So cognitive theory suggests that once knowledge frameworks or these things called schemas are acquired, we can use them for rapid learning. Using a variety of experimental techniques, we know that the prefrontal cortex learns task rules, the hippocampus performs one-shot association, and the motor cortex is involved in navigation. Although several deep learning models can show one-shot learning, they use biologically implausible learning rules like backpropagation of error signals. And that's why there's still a gap in bridging the theories of how one-shot learning happens and also how they're implemented in the brain. So this brings us to my thesis, which was to answer the question, how are these conceptual schemas represented in biologically plausible neural networks so that the networks or models can then perform one-shot learning? So the specific aim was to first develop a reinforcement learning agent that can gradually learn the multiple pet association task like the rats. And then subsequently, the idea is to extend this agent so that they can learn multiple new pet associations after just one trial. So let's start with the first objective, which is to develop a biologically plausible reinforcement learning agent that can gradually learn the multiple pet association task. So the multiple pet association task was simulated as a continuous 2D arena where the agent can freely move about. Then a one-hot encoded flavor cue is given to the agent as the input as well. The agent gets a reward only when it reaches the correctly cued goal location. The traditional solution is to use a model-free reinforcement learning algorithm such as the Actor Critic, where the agent learns a policy that specifies the action the agent has to take in the environment so that it can maximize the total reward. So Peter Dayan, Foster, and David Morris developed a canonical reinforcement learning agent that used spatially selective hippocampal place cells to encode the agent's location in the arena. So this is sort of breaking up or representing the XY coordinates of the agent in the arena using some sort of a bin representation. Then these place cells directly synapse to the actor and the critic components. So the critic learns the value map, which we show over here as a heat map, and this specifies which location has a higher propensity for reward. And the policy, which are shown by the arrows over here, so they specify what actions the agent needs to take in order to reach the reward. The synapses over here are modified using the temporal difference error modulated Hebbian learning rule, which is biologically plausible because it uses local presynaptic and postsynaptic information. And the temporal difference error is a global scalar modulatory factor. And this models the reward prediction error, which is signaled usually by the dopamine neurotransmitter. So to perform our multiple pet association task, I then modified the canonical agent by concatenating the Q vector with the place cell activity over here, and pass both of this information directly to the actor and the critic. We also introduced another agent where the place cell and Q information were first passed to a single non-linear feed-forward layer with the input synaptic weights drawn from a random uniform distribution. Then the activity of the single hidden layer was passed to the actor and critic correspondingly. So importantly, only the synapses from the hidden layer to the actor and critic were trained using the TDHL rule, and the input synapses were not touched. So these were kept random. Here we can see that the canonical agent, which was developed by Foster and is in orange, actually failed to learn the multiple path association task and only achieved chance level performance. So this is the orange one over here. Instead, only the agent with the non-linear hidden layer, which is the pink, gradually learned to navigate to the Q-specific goal locations and also showed increasing visit ratio performances like the rodents. And here we can see the difference in the trajectories learned by both the classical and also the agent of the non-linear hidden layer. So this is interesting because although the input weights to the single layer is fixed, the static single layer representation itself is sufficient to transform the place cell and sensory cue information for the actor and critic to learn different policies and different cues. Here we visualize the value and policy maps learned by the different agents. So for the canonical or the classical agent, they actually learn the same value and policy maps despite given different cues. Whereas the agent with the non-linear hidden layer learned distinct value and policy maps, as you can see over here. So this was what allowed the agent with the non-linear hidden layer to learn not just 6 path associations, but even up to 16 path associations as well. To understand what the non-linear hidden layer was doing, we changed several hyperparameters to look at how many principal components were needed to explain about 95% of the input stimulus. So this is shown in red. And also how many path associations the actor critic could learn out of 16. So that is shown in the green traces over here. So when the number of hidden units increased linearly, the dimensionality of the hidden layer actually increased rapidly, and the actor learned more path associates. Different activation functions influence learning performance, with ReLU performing the best and sigmoid performing the worst. We created 2 new activation functions called phi A and phi B. And these are analogs of the rectified linear unit or ReLU. And here we changed the threshold X so that the sparsity of the hidden layer representations increase. And this led to a corresponding increase in dimensionality. But as at the same time, after a certain threshold, this didn't lead to a proportionate increase in performance. So this peculiar relationship has been studied by several people, but we still don't have a strong understanding of why there's no correlation between sparsity, dimensionality, and also learning performance. So in the original rodent experiment, the flavor cues were actually given to the rats only in the start of the experiment, and the rats had to maintain this cue persistently throughout the navigation. Similarly, when we presented the cue only at the start of the trial, the agent with the single non-linear hidden layer, which is the one in pink, actually failed to learn the task because there's no sort of working memory to maintain this cue information throughout the trial. So instead, we included a bump attractor, which is able to persistently maintain the cue information using its bump attractor dynamics. As we can see over here, once we give the cue information at the start, because of the way the bump attractor is calibrated, then the cue information is then persistently maintained. We also replaced the single hidden layer with a reservoir network, which has some chaotic attractor properties as well. Here we can see that only the agents with the bump attractor actually solve the multiple path association task. And interestingly, the agent with the reservoir actually performed better than the agent with a single feed-forward layer. The dimensionality of the randomly connected reservoir was much higher than the single layer, but then again, we are not sure why the representations within the reservoir facilitated better learning performance. So after learning the multiple path association task, we then introduced the agents to 3 different pet association combinations for just 1 session, or like 1 trial for each of the new pet associates. So OPA is the original pet association, which is the same multiple pet association task. The 2 NPA, or 2 new pet association condition, has 2 of the new pet associates while having 4 of the original pet associations. Then the 6 NPA condition has 6 new flavor and location pet associations. So this is a more difficult form of the task where you need to learn all 6 within just 1 session. So given these 3 performances, or 3 different conditions, actually the current model, which is just the model-free actor critic, did not or was not able to learn the 2 or even 6 new pet associations after just 1 session. And this is because the gradually learned value and policy maps could not be adapted to the new pet associations after a single trial of learning. And this is because in a model-free reinforcement learning context, the synaptic weights are updated incrementally rather than just after a single trial. Okay, so we have come to the first interim conclusion. And so we started from the canonical agent and showed that by adding a single feed-forward or a recurrent layer, this helped to pre-process the place cell and sensory cue representations for the actor and critic to then gradually learn the multiple pet association task. So this is when the single layer weights were kept static. We have, as a separate experiment, we've also shown that a spiking network with a single hidden layer trained using the spike time dependent plasticity rule was also able to learn the multiple pet association task. So a spiking network is a more biological form of the rate coded network that we've been using over here. But this idea of using a single hidden layer to then expand the dimensionality to learn complex policies has been shown in these spiking networks as well. However, we've also shown that this model-free reinforcement learning agent is unable to learn multiple pet associations after just 1 shot, like the rats. So I'll just stop here for a while, and then maybe we can take some questions, and then we can move on to the next session.
Yeah, maybe I'll just start with the first question. And if anyone else like to ask anything on the first part, feel free to go ahead. I'm just curious. Last time you talked about the bump attractor, right?
Yep.
So is that something like an auto-associative memory where you have like different regions and you like through the cells conversing with one another, you reach a kind of memory?
Yeah. So the second part is right where the cells associate or are associated with one another to maintain the dynamics and persistently maintain the information there. So in a way, you can say that it's some sort of association. The idea of working memory is that there's no association that's learned over here. So it's purely based on the co-activation of neurons to maintain that information, right? So it's not associative in that sense. Yeah.
Okay, I see. So it's something like a hash table?
Something like a hash table, yes. So yes, you can say it in that case. But again, in a hash table, you have the benefit of adding information and deleting information. Whereas in this case, you can only put information in, and you don't have to do anything else, but that network is able to maintain that information throughout time.
I see. What about if you need to rewrite it? Will it affect the earlier memory?
Yeah, that's a good question. So with the current bump attractor setup, if you can see over here, when I pass Q1 in, and when we try to pass a new Q in, like for example Q8, sometimes there might be a possibility where the network maintains 2 separate informations, or it might forget the previous information and maintain a new information. So this dynamics, as of now, is unstable, or in the sense that I didn't stabilize it to maintain multiple new information, or it's so that's something that we can tune using the hyperparameters to determine what type of information you want to keep when you add new information in.
Thanks. Because I'm very interested in memory now, because I feel like memory is actually a way of learning. Other than reward mechanisms like the dopamine mechanism, actually using memory can actually condition yourself to do decisions in the future. So the way we store memory, the way we retrieve memory, I think now with like large language models, it's been shown that just using memory alone can already do cognitive agents. So I'm thinking that biologically we might have some form of like auto-associative. Over here, you use like a hash table that is a one-time storage. I'm thinking that if you have a memory module that is able to dynamically adapt to the environment, you might perhaps be able to learn multiple paired associations, not just at the start, but like as it changes, you can update the memory.
Yes, exactly. So that's the second part of the
Oh, sorry,
presentation.
I jumped a bit. All right. Okay.
Yeah. So at least it's good that you are already thinking of what's coming ahead. Yeah, exactly. Yeah. So that's the problem that we're going to solve next.
I have a second question. The
Yeah.
second question is, why do you think the non-linear is so important compared to like just having a linear feed-forward network to the actor and critic?
Yeah. So I mean, so experimentally, we see that it plays a part in this, in being able to learn multiple combinations. So the idea is that when we have place cells and sensory cues being passed together, that is a new code, a conjunctive code that is given. And from the experimentations, what is clear is that the actor struggles to learn distinct policies when we are having a linear network, because it basically jumbles up all of this information, and the representations can't be linearly disentangled if you're using a linear hidden layer. Rather, if you use a non-linear activation function, in the sense that the hidden layer is non-linear, then somehow the representations are much better separated. So the separability and the dimensionality is much higher, so that a linear decoder, in this case the actor, is able to learn distinct policies. So somehow having that non-linearity in the model linearizes that conjunctive code for the actor to then learn from.
Yeah, maybe it's better able to map in some abstraction space where it's more relevant with that non-linearity.
Yeah. So I mean, it's the same principle as in deep networks, right? Where we use non-linear activation functions to increase the complexity of the function that's learned. If not, the entire space is just compressed to a linear space if we don't have the non-linearity in the hidden layers. So that's something that was interesting when we discovered that having that single non-linear hidden layer allows linear classifiers, or in this case, a linear RL agent to learn multiple policies.
All right, thanks. Maybe I'll get 2 or 3 questions if anyone else wants to ask.
Yep.
Okay, I guess we have opportunities later as well. Yeah, so maybe
Sure.
we can move on first.
Okay. Okay, so yeah, we come to the next aim, which is to now determine what neural architectures and biologically plausible learning rules are needed to demonstrate this one-shot learning ability. So let's go back to the grocery shopping example. Once we are familiar with an environment, we are able to perform rapid navigation or one-shot navigation. So to do this, I think we need 3 different systems. The first is a GPS system that allows us to estimate our location in the market or in the arena or wherever environment or whatever environment that we're in. The second system is needed to rapidly store and recall goal information, something like a hash table. And the third system should be able to compute the shortest path to the goal wherever we are in the market. Right. So we need this sort of 3 different systems so that we can perform this one-shot learning. So the question is, how can this be biologically implemented in the brain? So let's start with the first system, the GPS system. So we know that, or from neuroscience experiments and sort of well-established theories, we know that the place cells and grid cells represent our position in an environment. However, these are binned representations. As we can see over here, these neurons fire only when the agent comes to this particular location, and these cells have different selectivity based on the location that they're in. So that's why we sort of call them as binned representation. And it has been shown that, or it has been suggested that these binned representations are actually not a suitable neural code to perform vector-based navigation. So instead, if we have a continuous metric representation of the environment, such as a X and Y coordinate system, we can then efficiently compute the vector displacement between our current coordinates and the goal coordinates to determine the direction of movement. So in fact, we can learn such a continuous metric representation from the binned place cell representation. So path integration is the ability to estimate our current X and Y coordinates using our previous coordinates and self-motion information. So for example, if I am taking a step forward, I can then do path integration to estimate where my new location is if I know my previous location and the action that I've taken. So that's the idea of path integration. So we can reformulate this path integration equation into a temporal difference error learning problem. We can then minimize this path integration TD error using a biologically plausible two-factor learning rule, which uses the place cell activity as the presynaptic term and the temporal difference error for each X and Y axis as a scalar signal. So this is such that as the agent explores the maze, the TD error is gradually minimized, and the agent learns the following X and Y axis representations, which the agent can then use to estimate its X and Y coordinates accurately for then self-localization. So as we can see here, initially the agent does not estimate its coordinates correctly, but as the TD error is minimized, we can see that after some time, the agent estimates that it's making a loop or in some sort of deviations in terms of its trajectory. Right, so this is one way that we think the brain is learning this sort of a GPS or coordinate-based system. So the second system needs to rapidly store and recall the Q and goal coordinate association. So this is where the hash table idea comes about, right? As the agent explores the maze, the agent should then store the coordinates at which it was rewarded as the goal coordinate. So in some sense, we can use a key value matrix or a hash table to store this Q vector in the key matrix and the coordinates at which a reward was dispersed in the value matrix. In a subsequent trial, when we get the same Q, we can use the similarity measure or the cosine distance rule to then recall the associated goal coordinates. But of course, this is a symbolic implementation as of now. So we need a more neural implementation of this hash table idea. So instead, we can pass the Q vector into a single layer network, and we can train the output synapses of the network using either a reward modulated perceptron rule or the exploratory Hebbian rule, which has been argued to be more biologically plausible because it uses a scalar teaching signal and local neural activity. Again, importantly, the plasticity of this entire learning rule is gated using the reward. So only when the agent receives a reward, that is when this plasticity or learning rule is activated and the association between the coordinates are formed.
Sorry, can I interrupt here for a while?
Yeah.
Yeah, because this is quite important for understanding. Like, because Hebbian rule is like neurons that fire together, wire together, right?
Yep.
Usually that's the explanation. Can you
Yep.
explain like how this equation models that?
Yeah. So the idea is, the idea of Hebbian learning is cells that fire together, wire together. It's a correlative learning rule. So usually it is in the context of a presynaptic neuron and a postsynaptic neuron. So that's where this correlation-based plasticity rule comes about. So this is the presynaptic term, and this is the postsynaptic term. So this is just a sort of average activity of the running term. So that's why this is still considered biologically plausible or Hebbian. So the only modification here, or the main thing about the Hebbian learning aspect, is that it is unsupervised in the sense that you do not guide what features or representations are learned because it's just based on correlations. But there has been additional work to show that Hebbian learning or Hebbian plasticity rules can be further modified to guide it in some sort of a supervised learning manner. So that is where we have a third factor. So this is the first factor, the presynaptic term. This is the second factor, which is the postsynaptic term. And we have a third factor, which is a scalar signal that informs us how close or how far is the current prediction from the true prediction. So this is like your mean squared error, your loss function, and that can be used as a scalar signal to then guide the Hebbian plasticity rule. So these three factors, or the third factor, is the one that converts this plasticity rule from unsupervised learning to a supervised learning rule. The only modification that we made over here is to add additional gating term using the reward signal, so that the entire factor is now a 4-factor learning.
Well, actually, it looks very similar to backprop, right? Like you only pass through the reward based on terms that are high in like value or high in magnitude. Like as you do the backprop, typically terms that are larger, and depending on the reward, will get backpropagated those those gradients so that you can change to go towards the reward. So like in here, your presynaptic, if it's greater than 0, or basically if it's magnitude is greater than 0, and your postsynaptic, if its magnitude is greater than 0, which is like the activation is greater than the average or more than the average, more than 0, then you backpropagate to those and update their weights. So I mean, it looks somewhat like backprop. Is that correct?
Yeah. So your first statement is right in the sense that you are you are sort of learning these associations based on the activation, right? Based on the presynaptic activation term. But in backpropagation, you do not consider the postsynaptic activity at all, right? Because you are computing the gradients based on the error, yes, but then you're computing the gradients based on the presynaptic term alone, without considering the postsynaptic activity. So that's the main difference between backpropagation and the Hebbian learning rule. And the other main difference is that this is temporal, right? So this is based on a time-based sequence, whereas backpropagation, there's no time component to it, right? So yeah, that's the main difference between backpropagation and this rule, where this is temporal, and this also uses mostly local information, which is just pre, post, and you have some sort of a global signal. So you're right in the sense that the global signal can be some sort of the error gradient, but here we don't do that. We don't need to compute the gradients with respect to the error.
Oh, actually, this is quite cool because you can do local error, as you said. So you don't have to backprop from all the way to an end to the start. You can just take the pre and the post and know your final reward. You can adjust the weights between the pre and the post activations.
Exactly. Yeah. Yeah. So you
then
can even
this,
skip through.
do you do this layer by layer, or like
no? So
how is this trained? Because this is something new to me as well. Yeah.
Yeah. So good question. So the good thing is that we don't need hierarchical layers or multiple layers in order to do this association. We only need to modify a single layer of synapses, as I showed over here. So this network is just a 3-layered network, right? Input, hidden layer, and output. So this is a super simple associative layer. There have been recent works, I think in 2019, in 2019 and 2021, where they showed that this idea of using a global error signal, and you can also modify both the output synaptic weights, and you can also modify the input synaptic weights, or even if you have a recurrent network, you can also modify the recurrent weights using that single global error signals, and you don't have to compute the error gradients. So that's quite cool. So you can check out that work as well. That's by John Murray, 2019. That is called local learning. Something about local learning rules of plasticity.
Yeah, definitely. I mean, this would be an alternative to backprop. I'm just wondering whether it has worked just as well. Yeah, because in the deep learning community, most people don't talk about it.
Yeah, exactly. So there have been new lines of work that are trying to merge, this sort of a reward modulated Hebbian learning rule and also backpropagation. Timothy Lillicrap has done some work in that, and that's where the idea of feedback alignment comes in. Right. Yeah. Cool. Okay. Are there any other questions about this part? I would say that this is the main part that does the one-shot association, which is needed for the agents to do one-shot learning. Okay. So here we have the one-shot association system, and we can compare this to other one-shot association systems like the Hopfield network or heteroassociative networks, right? So if you look at Hopfield networks, they actually collapse once the number of patterns exceed the critical capacity of 0.14 n. Instead, here we show that our network demonstrates a smooth stability and accuracy trade-off when we store up to 200 Q coordinate association pairs in just one shot. So after one shot association, we can see that the recall mean squared error is lower if we use a randomly connected reservoir, and that's in purple over here. And this is compared to if we use a single feed-forward layer instead of a reservoir network, and that's in red. So at the same time, the recall error is similar when we use the exploratory Hebbian rule, which is the more biologically plausible mechanism, compared to the force-based least mean squared error LMS rule, which is in brown over here. So actually, these are two very similar performances, although one is more biologically plausible. And of course, if we reduce the size of the hidden layer from 1024 units to 128 units, we can see that the recall mean squared error, which is in green and yellow, actually increase as the number of associations increase. So I just wanted to point out the difference between using a Hopfield network or using this sort of association network.
In other words, Hopfield networks are not good.
Yeah. Yeah, Hopfield networks, they suffer from this collapse. There are some other constraints as well. For example, from my experience, Hopfield networks, they don't perform well in continual learning tasks. So once you've stored a pattern in, and it's very hard to store new patterns in after you've set the weights in that case. So that's some of the difficulties that we encountered when using Hopfield networks. And that's why we came up with this, a more simplified implementation of associative network.
Yeah, it's quite funny because when I went to the Neurips workshop on memory in artificial and real systems, I think. Yeah, so basically in that workshop, like half the people use Hopfield networks or some modification of Hopfield networks. And I was thinking, I should go and try it out. I haven't tried it out yet, but based on what I see from your research, it looks like I shouldn't go towards that direction, because like it does look like it's not able to do this kind of one-shot learning if we use this not very plastic way of storing memory.
Yeah, exactly. So yeah, I mean, Hopfield networks are great to store memories, but it's very difficult to delete memories. And it's also difficult to add on new memories as we go with time. So there have been other networks that were proposed by a few other people. But from my perspective, these were not biologically plausible in the sense that they still require artificial manipulation of these memories. One fact that I didn't show over here is that over here, we are able to store memories in one shot, or these associations in one shot, but we are also able to delete these memories in one shot as well. So that's something that I didn't include in the slide, but it's in the paper over here, the 2023 archive paper. So we show that if we induce synaptic depression using some sort of acetylcholine. So this is where we use acetylcholine as the third modulatory factor, and we still use a Hebbian-like plasticity mode. We can actually delete Q-specific associations, such that when we delete one association, it does not affect the other associations. So that's something that was quite cool in the sense that we can now use this network to then write associations in one shot and also delete associations in one shot. And this is done in a more biological manner.
Oh, actually, that's quite cool. I mean, it's very similar. Eric Kandel's In Search of Memory. He did long-term depression and long-term, what's the other one? Long-term depression
potentiation.
and potentiation. Yeah, so it looks like yours can do both.
Yeah, that was the motivation over here. Yep.
Oh, very nice. And also, like, based on my experiments, also like forgetting stuff actually helps with performance. Like especially if you forget stuff that is irrelevant to your environment.
Exactly.
So I do think forgetting is a huge part of learning as well. So I'm glad yours can do that. Do this forgetting part.
Yeah, that's a good comment because in the next result I'm going to show why we need to forget memories. Yeah. Okay, so we've gone through the two systems, and the last system here is the navigation system, where the simplest way to move to a goal is by taking the shortest path. So this is by performing vector subtraction between the goal coordinates and the recalled goal coordinates, and also the agent's current coordinates. And using both of these coordinates, we can then compute the displacement vector and then choose the relevant actions to move in that trajectory. So this idea of vector-based navigation or computing the displacement vector is something that I think we learn since young, especially when a child is trying to move towards a toy, or when it's reaching out towards a toy or item to grab. Those are the periods in which we are learning this sort of vector subtraction ideas. So because of that, for the purpose of this work, we think we do not need to learn vector subtraction from scratch. And so we pre-train this network by backpropagation to learn vector displacement. So this is where this network takes in goal coordinates and the agent's current coordinates. We pass it to a 2-layer hidden network, and the last layer are actions that the agents need to take in order to navigate through that towards that goal coordinate. So this is just the simple vector displacement or vector subtraction, where we take the goal and we minus the agent's current position. Right. So this network, as I said, was pre-trained, but these networks, or the weights of these networks, were fixed during the entire course of the experiment in the next few results. Okay. So I've just described 3 different systems, and I think that these are important contributions to the field because these are the first few examples of how these ideas of theoretical schemas can be implemented using biologically plausible networks and learning rules. And therefore, I think that these computations could be also possibly be implemented in the brain for one-shot navigation. And so we have 3 different agents. The first is the actor critic from the first section. The second is a symbolic agent that still learns the continuous metric representation using place cells and then learning an XY coordinate. But in this system, the agent uses the symbolic key and value matrix, basically a hash table, to perform their one-shot association. And it also uses a symbolic navigate function. So without a neural network, it just performs the vector subtraction. The third agent is the fully neural schema agent, where we've composed the 3 different schemas that I mentioned before. So this is where the agent has place cells and sensory cue as input to the reservoir, and the output is trained to store and recall the goal coordinates. Then the place cells are used to also learn the continuous metric representation so that it allows the agent to self-localize like a GPS. Then we pass the agent's current coordinates and the recalled goal coordinates to the navigate schema, which then decides which direction the agent needs to move to reach the goal location. So coming back to the multiple paired association task, you can see that all 3 agents actually demonstrate gradual learning of the 6 original paired associations, what we saw in the first section. And here again, all 3 agents show increasing visit ratio performances. Then the agents were introduced to the 2 and 6 new paired associations for just once, or just one trial each. And as before, we can see that the actor critic, which is in pink, shows chance level performance for the 2 and 6 new paired associates. But here we can see that both the symbolic and the neural schema agents achieve above chance visit ratio performances, demonstrating the one-shot learning of 2 and 6 new paired associates. To also simulate being in a new environment, as you can recall from one of the first few slides, where we place a rodent in a new environment and it's not able to transfer that one-shot learning performance. So again here, after learning the 6 original paired associations, we scrambled the place cell selectivity to different regions of the arena. So now the X and Y representations that were gradually learned over here by the symbolic and neural agents could not be transferred over to the new maze. And because of this, the schema agents could not demonstrate one-shot learning in the new maze itself. So overall, all of these results actually replicate most of the rodents' learning behavior, both the one-shot learning and the inability to transfer their one-shot learning abilities to a new maze. So to determine the one-shot learning capacity of the schema agents, we introduced the trained agents to 12 new paired associations for a single trial, where the goal location was actually randomly sampled in the arena. So here we can see that the actor critic was only able to learn 1 paired association after just 1 trial, whereas the symbolic agent learned all 12 paired associations after 1 trial. I mean, this is expected because we are just using a hash table to store and recall the goal associations. Instead, when the neural agent only had 128 neurons, it learned only about 3 paired associations. But when the number of units was increased to about 1,000, the agent learned 9 paired associations after 1 trial. Agents with a randomly connected reservoir, which is in the yellow trace over here, actually learn more PAs than the agents with a single non-linear hidden layer, which is the green. The dip that we see over here is because of a difference in hyperparameters, because the learning rate was kept constant despite the change in the number of units. So actually, this was because the network was collapsing with a high learning rate. And so if we reduce the learning rate, actually the number of paired associations could be learned was about 9. So to make things harder for this agent, right, we introduce an obstacle in the center of the arena, as you can see here. And so that the agent needs to navigate past the obstacles to reach the goal. So this is particularly difficult because, as you can recall, the schema agents, their only mode of navigation was direct heading, right? Because you do vector subtraction and then you hit directly towards the goal. Whereas we know that Actor Critic actually learns policies that allows it to navigate past obstacles and reach the target eventually. The only downside is that Actor Critic weight updates are incremental, whereas is incremental and therefore they can't do one-shot learning. Whereas the neural schema agents are able to do one-shot learning, but they can't navigate past obstacles. So here we can see that the symbolic schema agents, which is the one in blue, actually struggles to learn these new paired associations or even the original paired associations because it only moves by direct heading. And so you can see that it gets stuck at most of the walls over here, right? So instead, now if we combine the Actor Critic over here and the schema agents, which is over here, into a single agent, now we call them as a hybrid agent. Now these hybrid agents are able to navigate past the obstacles, and they are also able to demonstrate one-shot learning of 2 and also 6 new paired associations. So this shows that there's that by combining the Actor Critic and the schema agents, this allows them to navigate past obstacles and also do this one-shot association. So we come to the last set of results. So this is where previously I've shown that a bump attractor is able to persistently maintain the cue information even though the cue is presented at the start of the trial. However, when a distractor is presented, this is where a different subpopulation of the bump attractor is activated, and this disrupts the working memory. So basically, you are asked to buy milk, but because you've seen a candy or toy, you forget to buy the milk and you buy the candy or toy instead, right? So theoretical works have suggested that the reward prediction error, which is indicated by DA or dopamine over here, this spikes when a task-relevant cue is given. So we can use this signal to learn a working memory gating policy, which opens to load the task-relevant cues into the bump attractor and close this gate so that distractors are not loaded into the bump attractor. So this is a very simple idea of gating working memory. So interestingly, such a gate can actually be trained using a biologically plausible 3-factor Hebbian rule that uses the reward prediction error as the modulatory factor. And we use the presynaptic term of the reservoir and the gating activity as the postsynaptic. So that's where the Hebbian learning rule, which is modulated by the dopamine, comes in. So for our final simulation, the reward prediction error, as you can see over here in purple, spikes when the cue is presented and is depressed when the cue is silenced. So after just one session of training, we can see that the working memory gate, which is in green, is equally likely to open or close when either the cue or the distractor is presented. But after 9 sessions of training, we can see that the gate actually learns a policy to open only when the cue is presented, and it remains closed when a distractor is presented. So when 2 distractors are presented and the synaptic plasticity for the gating mechanism is switched off. So this is the dark blue bar over here. This shows that the agent actually struggles to learn the original paired association task, the 6 original paired associations. And we compare this to the green bar where there are no distractors at all. So instead, if now we switch on the synaptic plasticity for the gating mechanism, let's look at the red bar over here, and we can see that the agent's ability to learn the multiple paired association task has been rescued, right? So from the blue to the red. So interestingly, this gating policy that was learned over 9 sessions actually generalizes to the 2 NPA and also 6 NPA conditions, such that the one-shot learning performance is also rescued, although the agent has only seen this new paired associations for just 1 trial. So we come to the second conclusion, and this is where we developed a scheme by taking a modular approach where each network has a different architecture and also uses different biologically plausible learning rules. We then compose these schemas together, and an agent can demonstrate one-shot learning of multiple new paired associations. At the same time, by combining the schema agents with the actor critic and the working memory gating component, this allows the agent to increase its robustness to other task conditions. But of course, there are several limitations of this work, and I hope this can be used as a basis for future directions as well. So firstly is the issue of biological plausibility. In this work, we have used mostly rate-coded neural networks and biologically plausible learning rules, but these are only approximations to how the brain computes. And so we need to use spiking networks and STDP learning rules to really demonstrate that these computations could really happen in the brain. So we've done that for the first section, and now we need to do some work to encode these schema-based networks into spiking networks. Next, the robustness of a proposed model depends on how well it generalizes to a variety of tasks. So we verified our agents on a subset of spatial navigation tasks, but we need to determine if it can also solve sequential navigation such as subgoals or solve hierarchical task structures instead of just paired associations, and also other cognitive tasks such as rule reversal and task switching. Next, our model is not constrained to neural data or brain regions, but is rather loosely mapped to the prefrontal cortex, the hippocampus, and striatal regions. So then again, I feel there's insufficient experimental evidence to guide the model development, and instead I hope that my model can serve as a theory for experiments to verify. Lastly, we know that episodic memory in the hippocampus is consolidated into the cortex as semantic memories, but this was actually not shown by our model. At the same time, there's still no established theory or algorithm of how memory consolidation happens. So this will be a really cool basis for future directions of future collaboration work to actually happen. So with that, I'll just take a pause here, and then maybe we can have a few more questions before we go to the last study, which is actually quite short. Yeah.
I have one question. I want to ask a bit more on the forgetting mechanism you mentioned briefly.
Right.
Is it also biologically inspired?
Yeah, definitely. So just to give a bit more clarity on that, the idea of biological plausibility is that the plasticity rules are governed by local information only. So you don't back propagate the information from somewhere else or some other layers. So this idea of forgetting, the equation is goes about where the weight change is governed by the presynaptic term multiplied by the postsynaptic term multiplied by a third term, which is just a negative scalar value. So that actually induces synaptic depression, where if you look at the paper over here, when we induce synaptic depression, this learned association actually goes back all to 0. So the association that was learned for Q4 actually all goes back or resets to 0. But the nice thing, as I mentioned, is that although we are deleting Q4 association, Q1s to Q6 information is still kept constant, and those are not affected.
So what phenomenon does it correspond to in our brain? Like, because it's hard for me to think of a concrete example where we can actively forget things. Like we choose to forget something, then we can forget.
Right. So okay. So that result was not. Yeah. Okay. So that result was not shown here. But so one task I would say is okay. One task I would say is imagine that you need to navigate in an arena, and you know that the milk is here, right? And so the idea is that if now the milk has been displaced, the market has moved the position of the milk to maybe the X area, then you would need to sort of delete the association and relearn an association over here.
So you update your information kind of.
Yeah, so you can update the information, or you can basically modify. The idea is to modify the previously formed association to a new form.
Okay, I see.
Yeah. Yeah.
Okay, thank you.
Yeah, thanks for the question. It's a relevant question. Yeah.
Yeah, maybe just adding on to that, in my learning fast and slow paper,
Yep.
I also did some memory forgetting by saying that if, let's say, there's an obstacle that is encountered in a path that was previously cleared, then that transition memory will be replaced by the obstacle. So I think it's very similar to that. Like we need to keep updating the representations of the world via updating the memory.
Right.
So in my opinion, a world model via weights of the neurons is implausible because it takes very long for weights to learn. But if you can build a world model by abstractions of the world space in your memory, and then you can use that memory to sort of do planning in the abstract space,
Yep.
then that is the world model already. It will be an abstract world model via memory reconstruction.
Right. Right. Yeah. So similar ideas. Yeah.
Also have one other point to note. When you talk about the gate to turn off the input representations.
Yep.
Is that also part of forgetting, or is just that is just interference, preventing interference?
Yeah. So in this case, I would say it's preventing interference.
Correct. I have a question about the experiment though.
Yep.
Like you only have interference after the main signal.
Yep.
And you see in the diagram with your gate has actually learned to tune out the signal after the first cue.
Yep.
All right.
Yep.
Just curious, if you have another cue subsequently, which I don't think you tested, will the gate learn to open? Or because this kind of gates, when you talk about weight updating, right, it takes very long for the weights to update. Backpropagation is kind of bad for fast learning.
Yep.
So my only concern is that after you learn to shut off the gate, it doesn't turn on again.
Right.
Yeah.
Yeah, no, good question. Yeah, so that's something that I wanted to test in the subsequent experiments. So actually this work is the first. So this idea has been a theoretical work, and people have shown this in a more symbolic representation context. So ours is the first neural implementation of this idea of gating working memory. Using biologically plausible networks. So definitely I would want to test if the gate can open in the subsequent when you present it subsequently. But from what I postulate, I would presume that yes, it will learn a policy to open up again when we show the cue subsequently, or we change the distractor such that we show the distractor first and then the cue comes on subsequently. So this policy is adaptable based on the rules of the environment.
I understand. But in this case, how would the agent know which is a cue and which is a distractor? Because the input format is the same, right?
Yes, correct. So yeah, exactly. So the cue here is, or the rule of the environment here is that the cue is always given at the start, and whatever follows are distractors. Like that has been always the way sort of neuroscience experiments has done, in the sense that they sort of simplify all of these working memory experiments. So like in my previous lab, that was one of the monkey experiments that we were doing, where you show the cue and then a distractor always follows. So that's the rule of how the cue and distractor happens. So when we want to mix between cue and distractors, and you need to learn which is the cue and which is a distractor, that is a next level complexity that I think this model won't be able to learn. And rather we need to learn a bit more sophisticated world models in order to distinguish between what is the cue and what is the distractor.
Probably how I envision it is that you need to ground the cue and the distractors in some form of context.
Yep.
And then from this context, tell whether or not it's a distractor or not. maybe through some attention mechanism. Like
Yeah.
you
Yeah.
attend to
Definitely.
like your past memory, and then you see, okay, this one doesn't make sense, so it's a distractor. This one makes
Yeah.
sense, so it's a.
Yeah.
So it may not be a weight updating thing. It might just be a comparison thing with memory.
Yeah. So I would say, yeah, exactly. So there was a paper by DeepMind, Jane Wang, 2018, called prefrontal as a meta reinforcement learning model or agent. So that paper shows that you can train a model using these ideas of dopamine or temporal difference error, and they learn this structure to compare what is the correct cue and what is a distractor. But then again, that was the model was trained using back propagation. And so there hasn't been a biologically plausible model for that yet. So that can be a whole new project by itself.
Yeah, you know, talking about DeepMind, I have a love-hate relationship with them. For one, DeepMind got me into research because of AlphaGo. I really like
Right.
like how they did superhuman stuff.
Right.
But then after I got into research, I realized that just using their way of training alone will take very long to train, and you will
Right.
only be very good for a very narrow specialized set of tasks.
Right.
Like Go, chess, or like
Yeah.
if you talk about Atari games, you need to train one separately for each game. Yeah, so
Yeah.
I realized that actually if you just use a reward signal,
Yeah.
like those kind of reinforcement learning algorithms with a reward signal and just purely just train it, it
Right.
takes very long to learn, and you will not have the generalization capabilities that we kind of want.
Right.
So
Right.
it seems to be that perhaps just a goal-directed learning would suffice. Like I
Right.
saw you did a goals minus the original cell. I think that's a good approach,
Yeah.
because I believe humans do goal-directed learning. I mean,
Yeah.
it's my learning path as well. So I think this is something that I think neuroscience is a bit slow to move away from, because everyone's still thinking that dopamine is the main thing of learning. Yeah, but what if dopamine is not really required for learning? I mean, this is just a controversial thing because everyone's talking about dopamine now. Yeah, so I'm just putting you out here. Yeah.
Yeah, I mean, it's a. I would agree that it's a controversial comment, because most of the learning, I mean, if you basically silence dopamine, it has been clearly shown that no learning happens, right? But the question is, what does the dopamine neurotransmitter encode? Is it just reward prediction error, or is it just reward? So that's the question that neuroscience has been trying to elucidate in the last few years. And we can start to see that actually the dopamine neurotransmitter encodes state prediction errors as well. So this is different from the reward prediction error. And the current theory is that dopamine encodes state prediction errors so that you can learn world models. What is the transition that's going to happen? What is the state transition that is going to happen? And what is the predicted next future state?
Yeah.
So
So
that is
maybe
what,
if I were to chime in, this is my view of dopamine, totally unscientific, but just my view. Dopamine determines when you should override your memory. So if your state that you see right now is different from the memory you store, your dopamine will be very high. You will override that memory with that new experience. And so when you next do your planning, you can just purely use your your memory stash to do the planning already to the goal that you want to do. Like, so the way you go to the goal itself has nothing to do with reward. It's just like heading towards the goal, maybe with a navigation module or like something that tries to utilize past memories to head to the goal. And dopamine could just be a way to, I don't know, a way to store memories or something. Yeah, so this is something that I was thinking of. Like I've been advocating reward-free like learning for a while.
Right. Yeah, I mean, I think it's definitely a point to discuss about. And yeah, as I said, people are sort of moving away from just looking at reward-based learning, and there has been associative-based learning, and also, as I said, state prediction error-based learning as well, where you're not learning based on a reward, but you're learning based on your estimation of what's the next state going to be. So yeah, I wouldn't constrain dopamine to just reward-based learning, but it has so many other properties that people are just only recently discovering it.
Yeah,
But
and
the
then, I
idea,
mean, we can talk more about this. This is a very controversial view. I think. Yeah. So yours is the more tried and tested approach. Yeah.
I mean, because we are developing models, we have to use past data and theories. But at the same time, what my model is also estimating is that there are some other mechanisms or learning signals that we need in order to perform these associations. So for example, going back to the learning rule over here, the scalar signal over here, we don't know what is. Like here, I've said it that it's just a scalar signal of getting close to the true association. But what encodes this scalar signal? That's something that we don't know what it is. It might be dopamine, it might be something else. Yeah. So there's still quite a lot of things that we need to verify through neuroscience experiments. And hopefully, yeah, that's why I said, experimentalists can try to use this model and either verify this or debunk this model.
Yeah,
But
actually,
I guess,
if you remove the gate plasticity with reward, do you try to remove that term, the gate plasticity with reward term?
Yeah, so if I remove that, then
Does it
the
still
idea,
learn? Yep.
no, so the idea is that you want to only associate when you get a reward. Because if you remove this term, then what happens is that the agent will then associate all of its coordinates to the queue itself. I mean, it
Understand.
might be something that happens, but yeah, so far in order to control the association, it's such that I don't want to remember, if I want to buy milk, I don't remember the path that I took to get the milk, but rather I sort of remember only the location in which the milk is placed. And then using that, I can then plan how my path or how am I going to reach the milk in the shortest path possible.
Is this reward signal a sparse reward signal of like 1 when you reach the goal and 0 otherwise?
Yes. Yep.
So actually, I also did something similar in fast and slow. So I call it reward free because you don't really need a reward for that. As long as what your intended goal is the same as your outcome, or your current position, you can just say, yes, I've reached my goal.
Right.
So
right.
I guess you can treat it as a form of reward, but it's going to be just an indication of whether the task is completed.
Yes, correct. Yep.
Yeah.
Exactly. Yeah. Similar ideas. Yep.
Yeah.
Exactly.
So the reward, as in like those kind of dance reward, you do reward shaping to make the robot move forward, that kind. I think those are just artificial hacks. Yeah, like about reinforcement learning.
Yeah, those are not sparse reward signals, but rather those are very informative reward signals. Whereas here we are
those
using
I like to call it like in the days where we don't have natural language models. These are ways to encode natural language into the robot by saying, hey, don't go too near the cliff, if not you'll fall down. So I give you negative reward near the cliff. That kind of stuff. Yeah.
Exactly.
But anyway, we should move on to your last part. Sorry for digressing.
No worries. I mean, discussion is always good. Okay, so just wanted to quickly share the new work that we've been working on. So as of now, we've been looking at biologically plausible algorithms for one-shot learning, but at the same time, I've sort of moved slightly away from that sort of a work, and now I'm working on computer vision projects. And we submitted this to ICCV, and we got fairly good reviews, so we'll know whether it gets accepted or not in 2 weeks' time. So this is a completely new set of paradigm, right? So this is where we are looking at the referring expression comprehension task, where we require models to identify the correct object in an image based on the query. So for example, if you look at the image on the right, we can see a blue statue and 2 birds sitting over here. So if I give the caption bird below the blue statue, the model needs to correctly identify the statue, the 2 birds, and then select or make its prediction such that it's the bird that is directly below the statue and not the bird that is beside the statue. So state-of-the-art deep learning models can actually achieve really good accuracies on these tasks, but they have very limited natural language vocabulary, and therefore the models have a superficial understanding of the query to perform this sort of a visual reasoning task. So instead, we humans, we use these things or word classes called determiners, which is a specific word class to refer to or quantify objects of interest. So for example, the semantics is completely different when we say, pass me that screwdriver compared to pass me my screwdriver. So we created this DetermiNet dataset, which contains synthetic images and captions containing determiners and nouns to then teach deep learning models the rules of determiners. So this figure shows the organization or the schema of 25 determiners with 4 subcategories, specifically articles, possessives, quantifiers, and demonstratives. So we had to define the rules for each determiner, as these rules were differently defined between different corpuses. But this was sort of our scheme or our organization of determiners and the rules of these determiners. So this is an example of the dataset, where if the query specifies this lemon, then the correct answer is the lemon closest to the camera's point of view and not the furthest lemon. But the complexity of the task increases exponentially, where there are actually multiple correct solutions. So for example, given the query either apple, the correct answer is to choose one apple and not both. So that's why this determiner task is actually not so trivial, right? So to test this idea of determiners, we developed a neurosymbolic model, which has a perfect object detector to extract all of the object bounding boxes and object classes from an image. It also has a perfect text encoder where the determiner and nouns are first encoded into two separate one-hot encoded vectors. Then all of the object bounding boxes and the one-hot encoded vectors are passed to a series of feed-forward networks, and the final layer selects the correct bounding box using an attention mask. So the network weights are all trained by backpropagation over here. So here we can see that the Oracle model, which has about 200,000 parameters, achieves about 93% on the DetermiNet task, while state-of-the-art models such as MDTR, which was developed by Meta, has about 18 million parameters, and this only attained about 70%. So the curve shows that both the Oracle model and the state-of-the-art models actually cannot learn the determiner rules with just a few examples, but require tons of data to get actually decent performance. Before training, this is the representation of determiners, and we can see that it's totally unorganized and random. But in the final layer or after training the Oracle model, we can see that there are actually well clustering of the neural representations when the network has to learn to solve the determiner with similar rules. So here we can see the dendrogram with the organization of the centroids, and we can see that the learned representations are rather similar to the conceptual organization or the schemas of determiners. So for example, these and those are closely grouped together. Your, my is grouped together, this and that, and then these are for quantifiers. So we can see that actually the network learns the rules or the organization of the determiners that I showed before based on how we curated the dataset and generated the dataset. So networks are able to learn these rules or this scheme as long as there's some sort of a statistical training regime. So we train the network on a synthetic dataset. Then we use these pre-learned determiner rules, and we see that these networks that were pre-trained on the synthetic dataset actually performed much better on a real-world dataset compared to the vanilla model. So that's where we see up to close to about 10% or 9% increase in performance because of training it on DetermiNet itself. But of course, the performance here is not as good, and this is because some of the weights were still not adapted from a synthetic dataset to a real-world dataset. But then again, the point of this experiment was to show that we can use these pre-learned rules to help the model make decent inferences or zero-shot inferences without much training subsequently. So this is just to conclude the last work, and we have shown that the neural networks can learn the rules or the schema of determiners and make decent inferences even on untrained datasets that have this sort of a DetermiNet-based task. However, this sort of a large vision models need tons of data to achieve decent improvements in performance. And because of this, the current paradigm of training large models end-to-end is actually not sample efficient. And so we need to think of other ways to train these sort of large models. So these are just some points to consider or things that I wanted to share from the works I've done. And yeah, so firstly, it is that we know that neural networks are great universal function approximators, and we can visualize these representations. But as we can see, they are not as efficient as we would like them to be. Especially, traditional training methods require a lot of data to learn a particular function or particular organization. So I think that to improve the efficiency of current networks, we can consider other factors, such as having adaptive thresholds to leverage on the benefits of a sparse coding regime. So this is where we have networks with high threshold or or neurons with high thresholds, or they have sparse coding regimes like in the brain. We can also consider recurrent architectures to learn non-linear manifolds or attractors compared to using just static linear or sort of a non-recurrent features. But of course, we need to develop rigorous analytical methods to really understand what these methods or networks are doing. Next, backpropagation of error gradients has been the best way to optimize these large networks, but it's really difficult to understand the computations that are performed by these deep layers and compare them to the brain computations. So instead, we can turn to more biological learning rules like Hebbian plasticity and self-supervised as a better solution for self-supervised or associative learning. So we can also consider other learning rules like anti-Hebbian or Sanger's rule to stabilize the network and also learn different types of representations for feature embedding. So there are quite a lot of papers suggesting that feedback alignment is almost as good as backpropagation to train deep networks, but it is also biologically plausible. So there has been some correspondence or convergence in ideas from the biological perspective and also deep learning perspective. And so I think there needs to be a bit more momentum to get some of these ideas rolling and works out. Then again, if you are really interested in the question of like biological plausibility, then we should be looking at spiky networks, which are extremely or sort of are really non-linear in its computation, and also spike time dependent plasticity to really hypothesize neural computations. And lastly, it is generally considered that biologically plausible models can only solve simple cognitive tasks. But if we can develop models using a modular network framework with single layers, then I think we can push the power of these biologically plausible models to solve even more complex tasks. So this is where we need to use different plasticity rules for each modules. And we can also look at various forms of supervised learning, unsupervised learning, and reinforcement learning to integrate all of these ideas together. So I think that going with that sort of a modular biological approach, we can better understand the neural computations, and these computations can be much more tractable in us trying to understand what is happening in these networks and also bridge the gap between biological and artificial systems. So before we end, I just wanted to share sort of two big questions that I've been pursuing through my research, not just now, but also in the future. So for example, the first question is, how does the brain represent abstract ideas? For example, things like linear algebra. So what are the inductive biases, associations, rules, or even schemas for learning and decision-making? And how are these represented in neural circuits? So we need to work with neuroscientists or experimentalists to then perform data analysis and understand how these computations are in the biological systems. In parallel, we also need to develop models that can replicate the behavior of animals and humans, and then determine if the neural computations are actually similar across these systems. The next question is, how can computation be flexible and also generative? So for example, once I know linear algebra, we can quickly understand that Fourier transformation is similar, or it fits into the scheme of linear algebra. We can also do the inverse, where we take a particular scheme like linear algebra and generate or deduce new combinations of concepts like Fourier transformation or other fundamental concepts in machine learning. So I've been always curious about how neural circuits or how our brain can achieve this, really flexible and combinatorial computations. And if we can answer that, then we can trickle down some of these ideas into models or artificial systems. So that's why for my research, the way in which I'm approaching my research is from two core elements. The first is using neuroscience to look at experimental evidence and then elucidate possible explanations for these neural computations. So for example, looking at neuromodulators, cognitive theories, and then we can use that to improve machine learning techniques and models. The second is to use machine learning techniques to develop new classes of learning algorithms, data analysis techniques, and also other analytical techniques. And this will help us better understand the computations that are happening in the biological system and see how can they generalize well to new contexts. So as we pursue these two sort of domains in parallel, then the aim is to develop algorithms for general intelligence and also develop other technologies to alleviate neurological disorders. So with that, yep, I would like to thank everyone for your attention, and yeah, happy to take any questions.
Yeah, thanks Ganesh for your great presentation. It really covers almost all the work he has done since undergrad days until now, or PhD days until now. And
Yep.
it's really very insightful because it is really exploring the fundamental nature of us, like what makes us learn, how do we learn these representations. You know, your questions of interest slide, I was quite happy because normally I also end off with a questions to ponder in my session. So it's
Right.
very
Okay.
yeah. So
Yeah.
I've asked quite a lot of questions just now already. Now I would like to just open the floor for all of you all here. Please go ahead and ask your questions. We do have like 10 to 15 minutes. Yeah. So without further ado, yeah, anyone can start asking.
Yes. Hi. I still have one more question. So just now you mentioned that the approach where do learning from by using mechanism more inspired by biology, right? It's so at the moment you can only do simple tasks. So do you have any comments on the scalability of such approach? Maybe in the near future.
Yeah, good. Great question. Yeah, so when I started my PhD, that was the main question or the main limitation I saw in biologically plausible models. But I'm happy to say that there have been some works to look at the scalability of this. So one work I would recommend checking out is this thing called feedback alignment. So as I mentioned, that's by Timothy Lillicrap, where he used some sort of Hebbian-like algorithms to train deep neural networks. So you train multiple or hierarchical layers of synapses, but you're using local synaptic rules and some sort of a global modulatory factor. So that has been one of the major works to unify the works between backpropagation and Hebbian learning. So check out his paper, Timothy Lillicrap, 2016, backpropagation in the brain, something like that. There have been a few more works by a few labs that are looking to scale up biologically plausible models as well. So another work is John Murray, 2019, training networks using local learning rules. So that's where he trained the input weights, recurrent weights, and the output weights using Hebbian-like plasticity again. Another lab is Gabriel Kryman. Not sure what is the year of the paper, so I think it's an ICML paper that looked at or proposed a new algorithm called Pepita. So that is an algorithm that is in between feedback alignment and Hebbian plasticity. So there have been a few more, as you rightly asked, there have been increasing amount of work that are looking at biologically plausible networks. One is to mimic the neural computations of the brain, and second, it is to understand what type of learning computations give rise to this sort of a flexible behavior. So I would say most of the works in machine learning have been looking at how do we learn representations. So the next phase of interest is going to be what type of algorithms are going to give us these brain-like computations or efficient learning computations. So that's going to be the next exciting 5 to 10 years of work that's coming up.
All right, thank you.
All right. Anyone else like to ask more questions? If not, maybe I'll ask mine first while you all think about it. Do take the chance to ask the questions, because I feel like the best way that we learn is when we discuss and share ideas like this. So this is the whole point of a live session. But anyway, my question is very, very interesting because I've actually seen a trend in your work that you are moving to a neurosymbolic kind of architecture. You have a symbolic oracle for, like, for example, your DetermiNet. You also have a symbolic way to do navigation, which, by the way, if you do like those kind of like flood view, not flood view, A-star search, or like those kind of depth search, you may not even need the actor critic if your symbolic agent knows how to do that. That's what they did in the Minecraft paper also, the Voyager paper. Their navigation module is like top notch. It can do all this kind of A-star search naturally.
Yep.
Yeah. So I'm just curious, what do you think is the way ahead for this kind of neurosymbolic architectures? Like especially in terms of like biologically plausible learning, yeah, and the stuff that we have been doing.
Right. Yeah, great question. I would say the point of symbolic algorithms is to really make it clear what computations are needed to perform this particular task. And so it's I would say they are super clear in terms of what really happens. So it gives us a very good perspective of what needs to happen and what are the computations that require in order to solve this task. So the point of using neurosymbolic is to I would say give us a bridge between the symbolic computations and also neural computations, right? Especially if the interest is to try to understand what the brain is doing. So for example, going to the last set of DetermiNet work, the idea is to see, or the question was to see, can neural networks learn the organization of schemas, right? So this was the organization that we set out to see if networks can learn. We created this organization and we can definitely encode this into a symbolic model, right? So that's not an issue. We actually generated individual rules, hard-coded these rules into a symbolic model. But yeah, as I said, the question is, how do networks represent this organization and how do they compute using this? Because if we can have some answers of that, then when we probe into the brain, the question is, can we see similar organizations? So in this dendrogram, then we can see that actually, yes, the networks do learn some sort of organization of the determinants. So then the natural question that we can ask is, okay, if these are how artificial neural networks are learning these organizations, is this how the brain is also representing this information in that space? If yes, then that's great. Then we have, or we are able to straddle between the symbolic, neurosymbolic, and the fully neural systems, right? And we can try to come up with a unifying framework to look at intelligence from that case. So that's why I prefer this symbolic, like a pure symbolic, then a neurosymbolic, and then a neural representation. And then we can try to work towards that general understanding of that unifying understanding.
Yeah, thanks. That's very insightful because my recent work I'm doing on the abstraction and reasoning corpus, that is actually neurosymbolic as well because I'm using the GPT to generate code. Code is somewhat like symbolic because you can do modules and rules. Yeah, so I've been also thinking like, is there a way for us to learn these rules naturally in the brain, like from experiences like, oh, I learned that if I go through door A, I'll meet a snake. So if door A, then don't go through that door. Could there be some form of behavior coded in some form of like if-then rules in the brain? And if so, like, how do we learn those blocks? Because those are fundamentally non-differentiable. You can't really use neural networks. You have to use a higher level of encoding, language or some system, which I don't think is very fully understood in neuroscience yet.
Yeah, exactly. Yeah, that's a great question. I mean, that's what we are working towards too. And yeah, exactly. Questions like if else, some sort of loops or sort of a Boolean transformations. I mean, these are things that we come from a symbolic computation point of view. I'm quite sure that the brain has either learned these computations in our lifetime, or these are already encoded as part of our proto programs when we were born with it, right? So yeah, then the fundamental question is, how are networks representing this if else statement? Is there a more efficient way of doing this, or more composable way of doing this computation, so that we can not just use that program as itself, but it's sort of connected to other programs. Let me try to think if there's a, yeah. So check out this paper by Robert Young, 2019. It's a Nature Neuroscience paper called Cognitive Clustering and Compositionality of Task Representation, something like that. So that is where they trained a single recurrent network to learn orthogonal tasks. So either a working memory task, but you have variations of the task, or you need to use learn controls. So that's where you say, if it is this rule, then you do this task. If it is this rule, you do this task. So it's a very symbolic way of writing the rules. But then the network learns a specific representation where these representations are shared between all the tasks. So it's not specific individual programs for each task, but these modules that it learns, it is shared between all these tasks. And so there's a negation, like there was a very nice module that performs negation based on the rule that was selected. Yeah, so that was quite a cool paper. Yeah, so that is how I think the brain learns this sort of symbolic computation, and is very good in modularizing all these networks so that it can determine, okay, at this task, I'm going to use these modules, and for that task, I'm going to use some other modules, but it's a combination of all these modules. Yep.
Yeah, very cool. At the higher level, it could just be very well network selection. Yeah, and this network selection could be learnable from experience. I mean, who knows, maybe there's some form of a reward signal backpropagated as well at the higher levels as it is in the lower levels, like the spatial modules, that kind of stuff. Like,
yeah. So I mean, that's what I think. So let's see if
you know, you read the brain thousand brains theory by Jeff Hawkins.
Right. Yeah.
He also thinks of like the brain, at least for his initial book on intelligence, he thinking that the brain is like hierarchical, like you have this small network, and then you use the same connections for the top level and so on. Yeah, I mean, more recently he refined his view. He said it's not that much hierarchy, and it's more like you have different input views, different ways of voting. But I quite like his first view better, like the hierarchy, but because I do think, like, even for memories exist at different hierarchies, and the way we process concepts are also going up this hierarchy.
Yeah, I would agree that I would think that hierarchy definitely exists. I mean, if you look at vision itself, as we go from the from V1 all the way to V4 and then the IT, there's that hierarchy that's encoded in terms of the representations that are learned. So I would definitely agree that there's hierarchy. I would think that the same happens for memory as well, where we start with episodic memories and then there's some sort of consolidation into semantic memories. So yeah, I mean, I would say that this idea of hierarchy definitely exists in the brain. Yeah, but then the question is, where does this hierarchy stop? And are there, parallel hierarchies that are also happening? Not just in terms of vision, are there in acoustics, in speech, in memory, and where do they all connect together? Some say it is in the prefrontal cortex, where you're sort of able to pull all of these pre-learned representations to then make new combinations. So that's why the prefrontal cortex is super interesting. Then again, the hippocampus is like the best or the fastest learner to make all this episodic information. So yeah, the brain is just super interesting, and it's hard to come up with a singular theory. But yeah, it would be cool to unify some of these ideas and test it and see that it works, and then we can apply these principles to machine learning and artificial systems.
Oh, yeah, that's very nice. I mean, the views are very similar to mine. Yeah, maybe before we end, because I think I've been hogging up a lot of time. Any other questions that anyone like to ask? Please feel free to ask now before we call it a day.
Oh yeah, I mean, if you have questions, yeah, feel free to just drop me an email or connect by LinkedIn or whichever it is. Yeah.
Okay, I guess we'll be ending, but definitely I think we will discuss more with Ganesh, because I do have some ideas about how memory actually helps with learning, and like how this eventually will lead to a neurosymbolic architecture. So I do think you will see the word neurosymbolic much more nowadays. Yeah, because that is probably the way ahead. And like multiple agents, we are seeing the word agents a lot nowadays in the large language model field. Agents, like what we saw in the earlier, the red navigation, you have a navigate agent. I mean, you have a symbolic agent, you have actor critic agent. All this can be used for different things. You can all combine them together. And yeah, there might be a way to do this meta level training by just seeing which agent is better for which task, and then you associate the agents to the tasks. Yeah, so I think there's a lot of future possibilities, not just from the neuron level, but also as a systems level. So eventually, all this together might solve like how the brain works.
Yeah, definitely. Yeah. So it's exciting times. Let's see what else comes out in the next few years.
Yeah, thanks so much, Ganesh, for presenting. And yeah, if you all do have any other questions, feel free to drop him a mail. And all those references that Ganesh mentioned earlier, I'll also be uploading it on the YouTube video so that y'all can take a look at the stuff like the local learning signals and so on.
Cool.
All right.
Yep. Thanks for having me. Yep. Take care. Yep.
Thanks. See ya, everyone.
Okay. Bye. Yeah.